In the last video for this week, we'll talk just a bit about bias in research. So let's start off with an example. In this study of 600,000 servicemen in the U.S. Army, Lazarsfeld found that men from rural backgrounds were able to adapt more easily to Army life compared to men from city backgrounds. So why do you think this could be the case? Can you think of any reason for why men from rural backgrounds would be able to adapt to Army life any better than city men? I seriously want you guys to pause this video and actually think about this and come up with a reason for why this might be the case. Okay, so now that you have your reasons, let's talk about what actually happened, which was the exact opposite. The actual findings from this study were that men from city backgrounds were able to adapt more easily to Army life than men from rural backgrounds. So I'll ask you once again, why? Can you think of a reason to predict this? Turns out that you can probably also find a reason to explain this result as well, and this exemplifies what we call hindsight bias. This kind of I knew it all along type of feeling. We've all heard the term hindsight is 20/20, and once we know the answer, the cause seems pretty obvious. Even more than that, what people think to be true is really difficult to put into question. And this is what you need to be able to do, is to evaluate research in a way that we're aware of our biases. So how do you reduce hindsight bias? Well, one way we've already talked about, which is to produce your hypothesis before you know any of the results. This way, if you're wrong, you don't change your answer, and it makes it a little bit easier to call into question what you originally thought to be true. We've talked about confirmation bias before, and you've watched that embedded video at the beginning of the course, but we'll touch on this again because it's an important one. There's a tendency to only seek out information that's consistent with your beliefs when you try to learn new things. This is evident by the fact that you don't see a lot of people really trying to prove themselves wrong. A lot of skeptics of the replication crisis said that their studies weren't going to be affected because they did everything right. But it was those same researchers who fell prey to confirmation bias. As researchers, you should really try to kill your theories. We should try to find every possible scenario that our experiments could fail, and you should try to exploit that. It should be only when our experiments stand tall from all of that we should be confident in the results. But it's definitely tough to overcome this, and that's why it's a bias in the first place, and that's why we talk about it. Being able to overcome this is important for science, and it's the basis for what we call null hypothesis significance testing, or NHST. We use this to find evidence against default conclusions. So no matter what we think, we use NHST to find evidence for an effect, whether you believe it to be true or not. So there's a cool example that works really well in an actual class where students can actually do this, but I think it still proves a point here. So I'll just run you through how it would actually work in a classroom. So I would give you a string of numbers like 6, 8, and 10, and I would ask you guys to generate numbers to test a particular rule of how those numbers are generated. Then I, as the experimenter, would only say yes or no to whether the numbers follow that rule or not. Then, after a few guesses, you're allowed to actually guess the rule. When we do this in class, we get some common guesses like 2, 4, 6, or 12, 14, 16, and I, as the experimenter, would nod my head yes. And then the guesses for the rule would be that, let's say, they increase by 2, or they all have to be even numbers. And that's not the rule, that's wrong. So the problem is that students are trying to seek answers that fit with the rule, where really they should be trying to generate numbers that would go against it or break the rule. Only that approach overcomes confirmation bias. So if we think the rule is that it increases by 2, we shouldn't guess 2, 4, 6. We should guess something like 2, 3, 4. Or if we think that the rule is that they're even numbers, we shouldn't guess 14, 18, 20. We should be guessing 14, 15, and 17. In the end, the correct rule turns out to be just that the numbers have to get bigger in general as they go on. So eventually a student would guess numbers in reverse or in descending order. And the experimenter would say, no, that doesn't follow the rule. And then the correct answer would be chosen. It's a cool demonstration to see in person because it shows just how long students will go trying to seek out answers that confirm their beliefs of the rule. Confirmation bias definitely happens in research, and it's where you seek out only information that supports your hypothesis. So that could be something like only reading articles from one side of the debate. In data collection, this could be something like asking biased questions or one-sided questions. Or in analysis, it could be only seeking out data that supports your conclusion and nothing against it. Another type of bias we come across is motivated reasoning. Sometimes large parts of the population fully reject widely accepted scientific findings, things like climate change or not accepting that vaccines do not cause autism. This is because people are more likely to reject a type of scientific finding when it conflicts with something in their worldview. People who don't smoke are more likely to accept the fact that smoking causes cancer. If you ask people who do smoke, however, they are more likely to not believe it or try and call that finding into question. This happens a lot in the general population, but it can happen to expert scientists as well. It happens to everyone. So to begin to wrap up, we can think about some steps to critical thinking. So when you hear a particular claim, step one is to be aware that the claim could potentially be false. Be skeptical about things. Step two, think about specifically in what ways this claim could be false instead of just saying it's fake and moving on. So review things you already know and also seek out additional information if necessary, especially things that might go against your beliefs. And step three, make a decision about whether you think the claim is true or false. But always remember that you could be entirely wrong. It's having this healthy level of skepticism, along with just being aware of our biases, that we can start to fight against it, which is a good approach to take for science.